when we talk about something being a solid, a liquid, or a gas, we know that it depends on the temperature as to what phase it happens to be in. It actually depends on both the temperature and the pressure. So this is what's called a phase diagram for water. So this is a phase diagram, and this is my sketch of the diagram in the book. It's figure, looks like in chapter 1, this is figure 12, 1.2. So this is a phase diagram. And what I want to do is just help you read it a little bit, because you can read these graphs, and I think it's useful to kind of just see how your general ability to read graphs can really lead you to some interesting information off of these graphs. Okay, so this is the gas phase, this is liquid, and then this is solid, and this is pressure versus temperature. And I want to put some points on here. Let's see, on the graph. So if the pressure is at about 1 atmosphere, like here, 1 atmosphere. I don't know that I've drawn this really to scale, but anyway, something like this. Then we know that when it goes from a solid to a liquid at 1 atmosphere, that's where we live. This is the line we live on. See, there's so much more information out there. Then that must be 0 degrees C, or 273 Kelvin. And this, the liquid to gas transition, we know happens at 100 C, right? So the solid directly to gas, right, like this is what we call sublimation. And of course, water doesn't do it, doesn't sublimate at atmospheric pressures. We do have some vapor, but yeah, that's CO2 does that, right? It goes from dry ice right into carbon dioxide. Liquid nitrogen, we're used to working with it in like a liquid form and seeing it boiling at room temperature. So its structure would be a similar kind of structure, but 1 atmosphere would not have us seeing a liquid nitrogen. It's just a gas for us at 1 atmosphere. This point is called the triple point because that's where all 3 exist. It's just there. For this, it's at a pretty low, it's really close to 0 C, so this is not to scale. This is at 0.1. Is it 0.1 or 0.01? Oh, it's 0.01, sorry, degrees Celsius. And this is pretty, not that low, but it's somewhat low pressure, 0.06 atmospheres. Okay, so one thing we can read no sublimation at where we live, which is this line, for example. But notice if we increase the pressure, we can increase the temperature of the liquid before we get to a gas phase. And so this is the idea behind pressure cookers, right? It moves you up, so up here, for example. And so the liquid, often water that you're boiling, for example, if you're making some kind of soup or just wanting to cook anything, mostly you're heating up the water in it, that's a higher temperature before it starts changing to a gas. Because if we're just boiling water open in a pot on the stove, then the highest temperature it's going to get to is basically 100 C if we're in Florida. Now, if you're somewhere high in the mountains and the pressure is a little bit lower, your boiling temperature is actually going to be lower, right? And that's why you have high altitude cooking information, because it's not that something weird happens at high altitude, it's just the boiling temperature is lower. You could fix everything by just using a pressure cooker, because then the temperatures would be the same, high altitude or low altitude. It doesn't matter once you're in a pressure cooker. So you can learn some interesting things from this, but one thing we know about making this transition from a solid to a liquid and then from a liquid to a gas is that it takes energy. So we know that we can heat things so that so that it causes a change in temperature. This is a heat that causes a change in temperature, right? That's built into the change in temperature. That's built into the equation. But when we do a phase change, it takes heat, we need some amount of heat that that tells us what it takes to change the phase. And it's given by the mass times this L, which is called your latent heat. It's just the heat needed for the phase change, and it can be of fusion or melting. So that's obviously this solid-liquid transition. So that's solid-liquid transition. Or the latent heat of vaporization or condensation, right? And that's going to be liquid-gas transition, right? Going from here to here or vice versa, right? And so this latent heat is just a property of the material that we're going to measure. We're going to look up on the table. It tells us how much heat is needed, so we can complete a full phase change. So you can put heat into a system and you can change its temperature, but if you're near a phase transition point, like if you have ice that started at like minus 15 C, you heat it up, you get it up to 0 C, then the heat is going to go into melting the ice before we can then start it along its line of heating up liquid and then maybe even going into steam, right? So these are all steps that ice would go through on its way to steam. It goes from ice, has to melt, so we need this. Then we have to use this to change its temperature up to 100. And then we need some more latent heat of vaporization to turn it into steam at that point. So if we're again trying to figure out if we have a glass of water and we're putting an ice cube in it, then we're asking what's the final temperature? Well, if we're left with water and a little less ice, but the ice isn't completely melted, then we know our final temperature is sitting here, because that's the point a solid and a liquid can be at equilibrium with each other. So that would be 0 C. If we have sort of, here's our water, we put some ice cubes in, the ice cubes melt, then you already know the temperature of the water slushy ice mix is at 0 C. Okay, if all of the ice isn't melted. And so then you can figure out, well, how much ice might be left, or how much ice do I need to cool my liquid down to 0 C, which is a nice, refreshing glass of ice water, right? That's what we like, at least when it's hot outside. And so we do these kinds of calculations. They're called sort of calorimetry problems, where we say that the heat that, when we bring these two together, the water and the ice, the heat of the hot object plus the heat that goes in, the heat lost, and the heat gained of the cold must equal 0. We talked about this last time. So if something is losing heat, this is a Q loss. It's useful to keep in mind this should be negative. So even though this doesn't have a sign, if something is giving up heat as it's making a transformation, like it's going from gas to liquid, so it's releasing heat, then that would be a negative value here. You really have to watch your signs. Whereas if you're gaining, that would be a positive value. So if you're ice and you're gaining heat to turn into liquid, then that would be a positive value here. Okay, so pay attention to which direction, whether you're losing heat or you're gaining heat. Okay, and when you go this direction on this plot, you have to gain heat, right? But if you go this direction, you're losing heat. So maybe that helps you out with keeping track of your signs. The signs fall out naturally on this equation, but on this equation, notice this can be our plus or minus, and that's determined by this. Okay, so just keep track of your signs when you're actually having to do basically energy conservation problems.